Now on Nova. Take a thrill ride into a world stranger than science fiction, where you play the game by breaking some rules, where a new view of the universe pushes you beyond the limits of your wildest imagination. This is the world of string theory, a way of describing every force and all matter, from an atom to Earth to the end of the galaxies, from the birth of time to its final tick, in a single theory, a theory of everything. Our guide to this brave new world is Brian Greene, the best-selling author and physicist.
And no matter how many times I come here, I never seem to get used to it.
Can he help us solve the greatest puzzle of modern physics? That our understanding of the universe is based on two sets of laws that don't agree. Resolving that contradiction eluded even Einstein, who made it his final quest. After decades, we may finally be on the verge of a breakthrough. The solution is strings. Tiny bits of energy vibrating like the strings on a cello. A cosmic symphony at the heart of all reality. But it comes at a price. Parallel universes and 11 dimensions, most of which you've never seen.
We really may live in a universe with more dimensions than meet the eye.
People who've said that there are extra dimensions of space have been labeled crackpots or people who are bananas.
A mirage of science and mathematics? Or the ultimate theory of everything?
The string theory fails to provide a testable prediction, then nobody should believe it.
Is that a theory of physics or a philosophy?
One thing that is certain is that string theory is already showing us that the universe may be a lot stranger than any of us ever imagined.
Coming up tonight, the undeniable pull of strings.
The atmosphere was electric.
String theory goes through a revolution of its own.
5 different string theories.
And reveals the new shape of things to come.
Perhaps we live on a 3-dimensional membrane.
Our universe might be like a slice of bread.
We're trapped on just a tiny slice of the higher dimensional universe.
That's actually a problem.
Watch The Elegant Universe right now.
And by the George D. Smith Fund and the U.S. Department of Energy, fostering science and security. Major funding for NOVA is also provided by the Corporation for Public Broadcasting and viewers like you. Thank you.
Imagine that we were able to control space, or control time. The kinds of things that we'd be able to do would be amazing. I might be able to go from here to here, to here, to here, and over to here in only an instant. Now, we all think that this kind of trip would be impossible, and it probably is. But in the last few years, our ideas about the true nature of space and time have been going through some changes, and things that used to seem like science fiction are looking not so far-fetched. It's all thanks to a revolution in physics called string theory, which is offering a whole new perspective on the inner workings of the universe.
String theory holds out the promise that we can really understand questions of why the universe is the way it is at the most fundamental level.
String theory is really the Wild West of physics.
This is an area of theoretical physics which is so radically different from anything that's been before.
This radical new theory starts with a simple premise that everything in the universe, the Earth, these buildings, even forces like gravity and electricity, are made up of incredibly tiny, vibrating strands of energy called strings. And small as they are, strings are changing everything we thought we knew about the universe, especially our ideas about the nature of space. To see how, let's first shrink all of space to a more manageable size. Imagine that the whole universe consisted of nothing more than my hometown, Manhattan. So now, just one borough of New York City makes up the entire fabric of space. And just for kicks, let's also imagine that I'm the CEO of a large corporation with offices on Wall Street. Because time is money, I need to find the quickest route from my apartment here in Upper Manhattan to my offices in Lower Manhattan. Now, we all know that the shortest distance between 2 points is a straight line, but even if there's no traffic, a bit of a stretch, even in our imaginary Manhattan, it'll still take us some amount of time to get there. By going faster and faster, we can reduce the travel time, but because nothing can go faster than the speed of light, there's a definite limit to how much time we can cut from our journey. This Manhattan universe fits with an old classical vision of space. Basically, a flat grid that's static and unchanging. But when Albert Einstein looked at the fabric of space, he saw something completely different. He said that space wasn't static. It could warp and stretch. And there could even be unusual structures of space, called wormholes. A wormhole is a bridge or a tunnel that can link distant regions of space. In effect, a cosmic shortcut. In this kind of universe, my commute would be a New Yorker's dream. But there's a hitch. To create a wormhole, you've got to rip or tear a hole in the fabric of space. But can the fabric of space really rip? Can this first step toward forming a wormhole actually happen? Well, you can't answer these questions on an empty stomach. Turns out that by looking at my breakfast, coffee and a donut, we can get a pretty good sense of what string theory says about whether the fabric of space can tear. Imagine that space is shaped like this donut. You might think that it would be very different from a region of space shaped like this coffee cup. But there's a precise sense in which the shape of the donut and the coffee cup are actually the same, just a little disguised. You see, they both have one hole. In the donut, it's in the middle, and in the coffee cup, it's in the handle. That means we can change the donut into the shape of a coffee cup and back again without having to rip or tear the dough at all. Okay, but suppose you want to change the shape of this donut into a very different shape, a shape with no holes. The only way to do that is to tear the donut like this, and then reshape it. Unfortunately, according to Einstein's laws, this is impossible. They say that space can stretch and warp, but it cannot rip. Wormholes might exist somewhere fully formed, but you could not rip space to create a new one over Manhattan or anywhere else. In other words, I can't take a wormhole to work. But now, string theory is giving us a whole new perspective on space, and it's showing us that Einstein wasn't always right. To see how, let's take a much closer look at the spatial fabric. If we could shrink down to about 1/millionth of a billionth of our normal size, we'd enter the world of quantum mechanics. The laws that control how atoms behave. It's the world of light and electricity and everything else that operates at the smallest of scales. Here, the fabric of space is random and chaotic. Rips and tears might be commonplace. But if they were, what would stop a rip in the fabric of space from creating a cosmic catastrophe? Well, this is where the power of strings comes in. Strings calm the chaos. And as a single string dances through space, it sweeps out a tube. The tube can act like a bubble that surrounds the tear, a protective shield with profound implications. Strings actually make it possible for space to rip. Which means that space is far more dynamic and changeable than even Albert Einstein thought. So, does that mean that wormholes are possible? Will I ever be able to take a stroll on Everest? Grab a baguette in Paris? And still make it back to New York in time for my morning meeting? It would be kind of cool, though it's still a very distant possibility. But one thing that is certain is that string theory is already showing us that the universe may be a lot stranger than any of us ever imagined. For example, string theory says we're surrounded by hidden dimensions, mysterious places beyond the familiar three-dimensional space we know.
People who've said that there are extra dimensions of space have been labeled as, crackpots or people who are bananas. I mean, what do you think there are extra dimensions? Well, string theory really predicts it.
What we think of as our universe could just be one small part of something much bigger.
Perhaps we live on a membrane, a three-dimensional membrane that floats inside a higher dimensional space.
There could be entire worlds right next to us, but completely invisible.
These other worlds would, in a very literal sense, be parallel universes. This isn't a particularly exotic or strange notion.
No wonder physics students are lining up to explore the strange world of string theory.
String theory is very active. Things are happening. There are a lot of people doing it. Most of the young kids, given the choice, at a ratio of something like 10 to 1, they will go into string theory.
But strings weren't always this popular. The pioneers of string theory struggled for years, working alone on an idea that nobody else believed in. Here's the gist of it. For decades, physicists believed that the tiniest bits inside an atom were point particles. Flying around the outside were the electrons, and inside were protons and neutrons, which were made up of quarks. But string theory says that what we thought were indivisible particles are actually tiny vibrating strings.
It's nothing really mystical. It's a really tiny string. It either closes into its little circle or it has endpoints, but it's just a little string.
In the 1980s, the idea caught on, and people started jumping on the string bandwagon.
Well, the fact that suddenly all these other people were working in the field had its advantages and its disadvantages. It was wonderful to see how rapidly the subject could develop now because so many people were working on it.
One of the great attractions of strings is their versatility. Just as the strings on a cello can vibrate at different frequencies, making all the individual musical notes, in the same way, the tiny strings of string theory vibrate and dance in different patterns, creating all the fundamental particles of nature. If this view is right, then put them all together and we get the grand and beautiful symphony that is our universe. What's really exciting about this is that it offers an amazing possibility. If we could only master the rhythms of strings, then we'd stand a good chance of explaining all the matter and all the forces of nature, from the tiniest subatomic particles to the galaxies of outer space. This is the potential of string theory, to be a unified theory of everything. But at first sight, in our enthusiasm for this idea, we seem to have gone too far. Because we didn't produce just one string theory, or even two. We somehow managed to come up with 5.
5 different string theories, each competing for the title of the theory of everything.
And if there's going to be the fundamental theory of nature, there ought to be one of them.
I suppose a number of string theorists thought, oh, that's fantastic, that's wonderful, and maybe one of these will end up being the right theory of the world. And yet there must have been a little nagging voice at the back of their head that said, well, why are there 5?
With 5 competing players, the stage of string theory was looking a little crowded. The 5 theories had many things in common. For example, they all involved vibrating strings, but their mathematical details appeared to be quite different. Frankly, it was embarrassing. How could this unified theory of everything come in 5 different flavors? This was a case where more was definitely less. But then, something remarkable happened. This is Ed Witten. He's widely regarded as one of the world's greatest living physicists, perhaps even Einstein's successor.
Ed Witten is a very special person in the field. He clearly has a grasp, particularly of the underlying mathematical principles, which is far greater than most other people.
Well, you know, we all think we're very smart, and he's so much smarter than the rest of us.
In 1995, string theorists from all over the world gathered at the University of Southern California for their annual conference. Ed Witten showed up at Strings 95 and rocked their world.
I was really trying to think of something that would be significant for the occasion. And actually, since 5 string theories was too many, I thought I would try to get rid of some of them.
To solve the problem, Witten constructed a spectacular new way of looking at string theory.
Ed announced that he had thought about it, and moreover, he had solved it. He was going to tell us the solution to every string theory in every dimension, which was an enormous claim, but coming from Ed, it was not so surprising.
The atmosphere was electric, because all of a sudden, string theory, which had been going through kind of doldrums, was given an incredible boost, a shot in the arm.
Ed Witten gave his famous lecture, and he said a couple of words that got me interested. And for the rest of the lecture, I got hooked up on the first few words that he said and completely missed the point of his lecture.
I remember I had to give the talk after him, and I was kind of embarrassed too.
Ed Witten just blew everybody away.
Ed Witten blew everybody away because he provided a completely new perspective on string theory. From this point of view, we could see that there weren't really 5 different theories. Like reflections in a wall of mirrors, what we thought were 5 theories turned out to be just 5 different ways of looking at the same thing. String theory was unified at last. Witten's work sparked a breakthrough so revolutionary that it was given its own name, M theory, although no one really knows what the M stands for.
What is the M for?
M theory.
M theory.
M theory.
M theory.
The M theory.
M theory is a theory.
I don't actually know what the M stands for.
Well, the M has...
I've heard many descriptions.
Mystery theory, magic theory.
It's the mother theory.
Matrix theory.
Monstrous theory. I don't know what Ed meant.
M stands for magic, mystery, or matrix, according to taste.
I suspect that the M is an upside-down W for Witten.
Some cynics have occasionally suggested that M may also stand for murky, because our level of understanding of the theory is in fact so primitive. Maybe I shouldn't have told you that one.
Whatever the name, it was a bombshell. Suddenly, everything was different.
There was a lot of panic, if you like, realizing that big things were happening and all of us not wanting to get left behind in this new revolution of string theory.
After Witten's talk, there was renewed hope that this one theory could be the theory to explain everything in the universe. But there was also a price to pay. Before M theory, strings seemed to operate in a world with 10 dimensions. These included 1 dimension of time, the 3 familiar space dimensions, as well as 6 extra dimensions, curled up so tiny that they're completely invisible.
Well, we think these extra dimensions exist because they come out of the equations of string theory. Strings need to move in more than 3 dimensions. And that was a shock to everybody, but then we learned to live with it.
But M theory would go even further, demanding yet another spatial dimension, bringing the grand total to 11 dimensions.
We know that there have to be 11 dimensions for this theory to make sense. So there must be 11 dimensions. We only see 3 plus 1 of them. How is that possible?
For most of us, it's virtually impossible to picture the extra higher dimensions. I can't. And it's not surprising. Our brains evolved sensing just the 3 spatial dimensions of everyday experience. So, how can we get a feel for them? One way is to go to the movies. We're all familiar with the real world having 3 spatial dimensions. That is, anywhere I go, I can move left, right, back, forth, or up, down. But in the movies, things are a bit different. Even though the characters on a movie screen look 3-dimensional, they actually are stuck in just 2 dimensions. There is no back, forth on a movie screen. That's just an optical illusion. To really move in the back-forth dimension, I'd have to step out of the screen. And sometimes, moving into a higher dimension can be a useful thing to do. So, dimensions all have to do with the independent directions in which you can move. They're sometimes called degrees of freedom. The more dimensions or degrees of freedom you have, the more you can do. That's right. And if there really are 11 dimensions, then strings can do a lot more too.
People found fairly soon that there were objects that lived in these theories, which weren't just strings, but were larger than that. They actually looked like membranes or surfaces.
The extra dimension Witten added allows a string to stretch into something like a membrane, or a brain for short. A brain could be three-dimensional, or even more. And with enough energy, a brain could grow to an enormous size, perhaps even as large as a universe. This was a revolution in string theory.
String theory has gotten much more baroque. I mean, now there are not only strings, there are membranes. People go on calling it string theory, but the string theorists are not sure it really is a theory of strings anymore.
The existence of giant membranes and extra dimensions would open up a startling new possibility. That our whole universe is living on a membrane inside a much larger, higher dimensional space. It's almost as if we were living inside a loaf of bread. Our universe might be like a slice of bread, just one slice, in a much larger loaf that physicists sometimes call the bulk. And if these ideas are right, the bulk may have other slices, other universes, that are right next to ours, in effect, parallel universes. Not only would our universe be nothing special, but we could have a lot of neighbors. Some of them could resemble our universe. They might have matter and planets and, who knows, maybe even beings of a sort. Others could certainly be a lot stranger. They might be ruled by completely different laws of physics. Now, all of these other universes would exist within the extra dimensions of M-theory, dimensions that are all around us. Some even say they might be right next to us, less than a millimeter away. But if that's true, why can't I see them or touch them?
If you have a brain living in a higher dimensional space and your particles, your atoms, cannot get off the brain, it's like trying to reach out, but you can't touch anything. It might as well be on the other end of the universe.
And it's a very powerful idea, because if it's right, it means that our whole picture of the universe is clouded by the fact that we're trapped on just a tiny slice of the higher dimensional universe.
It is a powerful idea, especially because it may help solve one of the great mysteries of modern science. It has to do with gravity. It's been more than 300 years since Isaac Newton came up with the universal law of gravity, inspired, as the story goes, by seeing an apple fall from a tree. Today it seems obvious that gravity is a powerful force.
It would seem to most people that gravity is a very important force. It's very strong. It's very hard to get up in the morning, stand up, and when things fall, they break because gravity is strong. The fact of the matter is that it's not strong. It's really a very weak force.
Gravity pulls us down to the Earth and keeps our Earth in orbit around the sun. But in fact, we overcome the force of gravity all the time. It's not that hard. Even with the gravity of the entire Earth pulling this apple downward, the muscles in my arm can easily overcome it. And it's not just our muscles that put gravity to shame. Magnets can do it too. No sweat. Magnets carry a different force, the electromagnetic force. That's the same force behind light and electricity. It turns out that electromagnetism is much, much stronger than gravity. Gravity, in comparison, is amazingly weak. How weak? The electromagnetic force is some 1,000 billion, 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 billion times stronger. That's a 1 with 39 zeros following it. The weakness of gravity has confounded scientists for decades. But now, with the radical world of string theory, filled with membranes and extra dimensions, there's a whole new way to look at the problem.
One way of approaching the question of why gravity is so weak compared to all the other forces is to turn the question completely on its head and say, no, actually, gravity isn't very weak compared to all the other forces. It just appears to be weak.
It may be that gravity is actually just as strong as electromagnetism, but for some reason, we can't feel its strength.
Consider a pool table, a very large pool table. Think of the surface of the pool table as representing our three-dimensional universe, although it is just two-dimensional. And think of the billiard balls as representing atoms and other particles that the universe is made out of.
So here's the wild idea. The atoms and particles that make up stuff in the world around us will stay on our particular membrane, our slice of the universe, just as the billiard balls will stay on the surface of the pool table. Unless you're a really bad pool player. But whenever the balls collide, there is something that always seeps off the table. Sound waves. That's why I can hear the collision. Now, the idea is that gravity might be like the sound waves. It might not be confined to our membrane. It might be able to seep off our part of the universe. Or, think about it another way. Instead of pool tables, let's go back to bread. Imagine that our universe is like this slice of toast, and that you and me and all of matter, light itself, everything we see, is like jelly. Now, jelly can move freely on the surface of the toast, but otherwise it's stuck. It can't leave the surface itself. But what if gravity were different? What if gravity were more like cinnamon and sugar? Now, this stuff isn't sticky at all, so it easily slides right off the surface. But why would gravity be so different from everything else that we know of in the universe? Well, it turns out that string theory, or M theory, provides an answer. It all has to do with shape. For years, we concentrated on strings that were closed loops, like rubber bands. But after M theory, we turned our attention to other kinds. Now we think that everything we see around us, like matter and light, is made of open-ended strings. And the ends of each string are tied down to our three-dimensional membrane. But closed loops of string do exist. And one kind is responsible for gravity. It's called a graviton. With closed loops, there are no loose ends to tie down, so gravitons are free to escape into the other dimensions, diluting the strength of gravity and making it seem weaker than the other forces of nature. This suggests an intriguing possibility. If we do live on a membrane, and there are parallel universes on other membranes near us, we may never see them. But perhaps we could one day feel them through gravity.
If there happens to be intelligent life on one of the membranes, then this intelligent life might be very close to us. So theoretically, and purely theoretically, we might be able to communicate with this intelligent life by exchanging strong gravity wave sources.
So, who knows? Maybe someday we'll develop the technology and use gravity waves to actually communicate with other worlds. Yeah, hey, it's Brian. How you doing?
Brian. Woofa Jubby Woofalapa Jabba Simpsons.
We don't really know if parallel universes could have a real impact on us. But there is one very controversial idea which says they've already played a major role. In fact, it gives them credit for our existence.
As the classic story goes, the vast universe we see today was once extremely small, unimaginably small. Then, suddenly, it got bigger. A lot bigger during the dramatic event known as the Big Bang. The Big Bang stretched the fabric of space and set off the chain of events that brought us to the universe we know and love today. But there's always been a couple of problems with the Big Bang theory. First, when you squeeze the entire universe into an infinitesimally small but stupendously dense package, at a certain point, our laws of physics simply break down. They just don't make sense anymore.
The formulas we use start giving answers that are nonsensical. We find total disaster. Everything breaks down. And we're stuck.
And on top of this, there's the bang itself. What exactly is that?
That's actually a problem. Classic form of the Big Bang theory really says nothing about what banged, what happened before it banged, or what caused it to bang.
Refinements to the Big Bang theory do suggest explanations for the bang, but none of them turn the clock back completely to the moment when everything started.
Most people come at this with the naive notion that there was a beginning, that somehow space and time emerged from nothingness into somethingness.
Well, I don't know about you, but I don't like nothing. Do I really believe that the universe was a big bang out of nothing? And I'm not a philosopher, so I won't say, but I can imagine to a philosopher that is a problem. But to a physicist, I think it's also a problem.
Everyone admits there are problems. The question is, can string theory solve them? Some string theorists have suggested that the Big Bang wasn't the beginning at all, that the universe could have existed long before, even forever. Not everyone is comfortable with the idea.
I actually find it rather unattractive to think about a universe without a beginning. It seems to me that a universe without a beginning is also a universe without an explanation.
So what is the explanation? What if string theory is right, and we're all living on a giant membrane inside a higher dimensional space?
One of the ideas in string theory that was particularly striking to me and suggested perhaps a new direction for cosmology is the idea of brains and the idea of brains moving in extra dimensions.
Some scientists have proposed that the answer to the Big Bang riddle lies in the movements of these giant brains.
It's so simple. Here's a brain on which we live, and here's another brain floating in the higher dimension. There's absolutely nothing difficult about imagining that these collide with each other.
According to this idea, sometime before the Big Bang, two brains carrying parallel universes began drifting toward each other. Until
all of that energy has to go somewhere. Where does it go? It goes into the Big Bang. It creates the expansion that we see, and it heats up all the particles in the universe in this big fiery mass.
As if this weren't weird enough, the proponents of this idea make another radical claim. The Big Bang was not a special event. They say that parallel universes could have collided not just once in the past, but again and again. And that it will happen in the future. If this view is right, there's a brain out there right now, headed on a collision course with our universe.
So another collision is coming, and there'll be another Big Bang, and this will just repeat itself for an indefinite period into the future.
It's an intriguing idea. Unfortunately, there are a few technical problems.
Well, that was a very ingenious scenario that arose naturally within string theory. However, the good old problems creep back in again.
The fact is, we don't really know what happens when two brains collide. You can wind up with the same situation we had with the Big Bang. The equations don't make sense.
They have to make a lot of assumptions in their models, and I don't think they've really solved the problem of the Big Bang in string theory.
If string theory is the one true theory of the universe, it will have to solve the riddle of the Big Bang. And there's a lot of hope that someday string theory will succeed. But for now, there's also a lot of uncertainty. As promising and exciting as the theory is, we don't entirely understand it.
It's as if we've stumbled in the dark into a house, which we thought was a 2-bedroom apartment, and now we're discovering is a 19-room mansion, at least, and maybe it's got 1,000 rooms, and we're just beginning our journey.
So, how sure are we that the universe is the way that string theory describes it? Is the world really made up of strings and membranes, parallel universes, and extra dimensions? Is this all science or science fiction?
Well, the question we often ask ourselves as we work through our equations is this just fancy mathematics, or is it describing the real world?
These exercises in our imagination and mathematics are all, at the end of the day, subjected to a single question. Is it there in the laboratory? Can you find its evidence?
String theory and string theorists do have a real problem. How do you actually test string theory? If you can't test it in the way that we test normal theories, it's not science, it's philosophy. And that's a real problem.
Strings are thought to be so tiny, much smaller than an atom, that there's probably no way to see them directly.
But even if we never see strings, we may someday see their fingerprints. You see, if strings were around at the beginning of the universe, when things were really tiny, they would have left impressions or traces on their surroundings. And then, after the Big Bang, when everything expanded, those traces would have been stretched out, along with everything else. So, if that's true, we may someday see the telltale signs of strings somewhere in the stars.
But even here on Earth, there's a chance we can detect evidence of strings. This past year in Illinois serves as command central for a lot of this research. Well, actually, the real work happens underground, where the hunt is on for evidence supporting string theory, including extra dimensions.
Not too many years ago, people who talked about large extra dimensions would have been considered crackpots, to put it lightly.
But all that has changed, thanks to string theory. This is Fermilab, and right now, it's our best hope for proving that extra dimensions are real. Fermilab has a giant atom smasher. Here's how it works. Scientists zap hydrogen atoms with huge amounts of electricity. Later, they strip them of their electrons and send the protons zooming around a 4-mile circular tunnel beneath the prairie. Just as they're approaching the speed of light, they're steered into collisions with particles whizzing in the opposite direction. Most collisions are just glancing blows, but occasionally there's a direct hit. The result is a shower of unusual subatomic particles. The hope is that among these particles will be a tiny unit of gravity, the graviton. Gravitons, according to string theory, are closed loops, so they can float off into the extra dimensions. The grand prize would be a snapshot of a graviton at the moment of escape.
And then the graviton goes to the extra dimension, and then it shows in the detector by its absence. You see it by its absence.
Unfortunately, Fermilab hasn't yet seen the vanishing graviton. And the pressure is on, because another team is hot on the same trail. "4,000 miles away, on the border of France and Switzerland, a lab called CERN is constructing an enormous new atom smasher. When it's finished, it will be 7 times more powerful than Fermilab's.
There's a great sense of urgency that every minute has to count, but eventually CERN, our rival laboratory, will, frankly, blow us out of the water.
CERN will blow Fermilab out of the water not only in the search for extra dimensions, but other wild ideas.
At the top of the to-do list for both labs is the hunt for something called supersymmetry. That's a central prediction of string theory, and it says in a nutshell that for every subatomic particle we're familiar with, like electrons, photons, and gravitons, there should also be a much heavier partner called a sparticle, which so far no one has ever seen. Now, because string theory says sparticles should exist, finding them is a major priority.
So it's a big discovery to find supersymmetry. That's a humongous discovery, and I think it's a bigger discovery to find supersymmetry than to find life on Mars.
If we were to hear tomorrow that supersymmetry was discovered, there would be parties all over the planet.
The problem is, if they exist, the sparticles of supersymmetry are probably incredibly heavy. So heavy that they may not be detected with today's atom smashers.
The new facility at CERN will have the best chance once it's up and running in several years. But that won't stop the folks at Fermilab from trying to find them first.
The competition is friendly and fierce at the same time. We're competing like bad dogs, essentially. And it has always been like that, and it will always be like that.
We have to make sure that we don't make any mistakes, that we do absolutely the best we can do with these experiments, and take advantage of what is really one of the great golden opportunities for discovery.
If we do find sparticles, it won't prove string theory, but it will be really strong circumstantial evidence that we're on the right track. Over the next 10 to 20 years, the new generation of atom smashers is sure to uncover surprising truths about the nature of our universe. But will it be the universe predicted by string theory? What if we don't find sparticles or extra dimensions?
What if we never find any evidence that supports this weird new universe filled with membranes and tiny vibrating strings? Could string theory, in the end, be wrong?
Oh yes, it's certainly a logical possibility that we've all been wasting our time for the last 20 years and that the theory is completely wrong.
There have been periods of many years where all of the smart people, all of the cool people were working on one kind of theory, moving in one kind of direction, and even though they thought it was wonderful, it turned out to be a dead end. This could happen to string theory.
Even though there's no real evidence yet, so much of string theory just makes so much sense. A lot of us believe it's just got to be right.
I don't think it's ever happened that a theory that has the kind of mathematical appeal that string theory has turned out to be entirely wrong. I would find it hard to believe that that much elegance and mathematical beauty would simply be wasted.
I don't really know how close we are to the end. Are we almost there and having the complete story? Is it going to still be another 10 years? Nobody knows. I think it's going to keep me busy for a long time.
We have been incredibly lucky. Nature has somehow allowed us to unlock the keys to many fundamental mysteries already. How far can we push that? We won't know until we try.
A century ago, some scientists thought they had pretty much figured out the basic laws of the universe. But then Einstein came along and dramatically revised our views of space and time and gravity. And quantum mechanics unveiled the inner workings of atoms and molecules, revealing a world that's bizarre and uncertain. So, far from confirming that we had sorted it all out, the 20th century showed that every time we looked more closely at the universe, we discovered yet another unexpected layer of reality. As we embark on the 21st century, we're getting a glimpse of what may be the next layer. Vibrating strings, sparticles, parallel universes, and extra dimensions. It's a breathtaking vision. And in a few years, experiments may begin to tell us whether some of these ideas are right or wrong.
But regardless of the outcome, we'll keep going because, well, that's what we do. We follow our curiosity. We explore the unknown. And 100 or 1,000 years from now, today's view of the cosmos may look woefully incomplete, perhaps even quaint. But undeniably, the ideas we call string theory are a testament to the power of human creativity. They've opened a whole new spectrum of possible answers to age-old questions. And with them, we've taken a dramatic leap in our quest to fully understand this elegant universe.
On NOVA's website, go behind the scenes with Brian Greene. Journey into the subatomic world. Play with strings. Picture other dimensions and much more. Find it on pbs.org. To order this program on VHS or DVD, or the book The Elegant Universe, please call WGBH Boston Video at 1-800-255-9424.